All right, so a quick review on the multimeters. I am drilling this thing a little bit, and the reason for that is, let me just get the screens that I need. There we go. The reason for that is that I want you to be comfortable with the basic tools that you will be using as future electricians or any thing that has to do with electronics, electricity. You never know where the road is going to take you. But this is a good start. And it would be just funny if we let you out of this college without the knowledge of the simple, basic, crucial things that you need to know. And one of them is using something like a multimeter. Well, we need to use that. So I want to make you as comfortable as possible while using different types of measuring equipment. And today I'm just going to quickly review the analog scale. We haven't, well, we have on the video that I posted, but this is going to be just a review, just so this thing sets in you, so you're as comfortable as possible. All right, so what do we have on this screen? We have an example. I glued together, copy and pasted different pictures in order to simulate well, how the multimeter works. So this particular one doesn't exist. I just cut and paste from different multimeters. So, all right, what do we see here? Basic things. We see scales on this. And where do we look? Where do we look when the needle swings out? All right, so the top scale right here, what you could see is, well, what is that scale? There's some numbers on it, and on the left, there's that infinity sign. It looks like a horizontal um, 8. All right, but it's the ohms. Well, this symbol here is for infinity. The omega symbol is right here, and that represents the ohms, um, which stands for resistance. Now, right underneath, we have some kind of like a gray strip, and really what it is supposed to be a mirror. The reason for the mirror to exist is that you are supposed to look straight down the needle, because the needle is offset a little bit. It stands off. It doesn't touch the scale, so there's a tiny bit of a distance between the needle and the graphics and the scale. So if you look at it under an angle, you will see that needle against something else that it actually points to. So you need to look at it straight down, and the mirror is going to help you with that, because if you look straight down, you match the reflection of the needle, and you cover the reflection with the needle with actual needle by adjusting the way you look at it, and that means you're going to look at it straight down, and you read the exact spot that the needle points to. Right, so that's the gray little thing here. It's a mirror. Right, now we have another scale that it has a bunch of divisions and whatnot. There's an explanation here. This one here, and it's in red, it's supposed to use DC volts and amps, right? Voltage and amperage, voltage and current. So these three scales, scales correspond to this, graphic divisions representation. Like, for example, this division right here corresponds to number 6, number 30, and number 150. Well, what does it mean? Well, here's a top scale that goes from 0 to 10. So that's the 0 to 10 scale. On the bottom, here's a 0 to 50. You can choose that scale to get your reading, or there's another one here that is from 0 to 250, and sometimes you want to use that scale. Depending on which scale you choose, the divisions are going to represent different quantities, right? Like, for example, here's a scale of 0 to 10. how can we figure out what it is from 0 to 10? Here is 0, here is 2. Well, so over here, obviously this is going to be 1. How many divisions? 1, 2, 3, 4, 5 divisions between 0 and 1. So let's say if we go 0 0.2, 0 0.4, 0 0.6, 0 0.8, 10, 0 0.10, right? So it's 1 or 1.0. So here's 1, 1.2, 1.4, 1.6, 1.8, 2, and so on. This is how you read the divisions on the scale of 1 to 10. Let's look at the 0 to 50. Well, we got from 0 to 10. So over here is going to be 5. So how can we get to 5? Let's see what the smallest division represents. If this is 5, it's 1, 2, 3, 4. Oh, well, you know, if this is 0 to 50, and this is 1, sorry, this is 10, so this is 5. So let's say 1, 2, 3, 4, 5. Okay, well, each division is going to represent 1, the number 1. All right, and so on. 10, 11, 12, 13, 14, 15 here, and between, of course, between 10 and 20 is 15. So in that case, now let's see 250. Here's 0 to 50, so that's going to be 25 here. Well, what's the smallest division number? If this is 0 to 50 and this is 25, let's see. Let's try this. 5, 10, 15, 20, 25, 30, 35, 40, 45, 50. So that's how we can understand the different scales depending on which numbering divisions we apply. All right. Now on the bottom here is the red scale in red, and in this particular meter, this is supposed to serve as the scale to measure AC voltage. Right? I guess this meter is not capable of whatever I cut and paste from. This meter is not capable of measuring current. Well, sometimes, but most of the times you will. I just grabbed some scale just to show you the idea how to use the scale. All right, well, here is also the dial that we could set the ranges, and in this particular one, there's that off position. So let me just choose the dial here and turn the dial right to the off position. Right. Now, right off the bat, when there's nothing connected to the meter, you are going to have the needle sitting at position something like this, just like that. If you take it out of the box or out of your storage, you're going to see something like that. Now, it's not exactly wrong. Yeah, it's not exactly sitting at 0, is it? All right. Well, what we do is just to sort of give it a bit of a calibration. Here is the adjusting screw. So sometimes the 10-cent coin works, but a small slotted screwdriver works pretty fine. So it's a mechanical adjustment, and what you will do is just be turning that slightly in order to bring the needle to the 0 position. And if you do that, you're going to bring it to something like, well, turning the screw, and you're going to get this thing right to here. All right, cool. So now we have calibrated this thing mechanically. Now, when it comes to measuring resistance, notice one thing. All the scales start from 0 to whatever the maximum number of the scale is to the right, except for the resistance scale. Look at this. The resistance starts at infinity on the left instead of 0, and as it swings out, it brings to 0. Well, that's because in order to measure the resistance, remember, the meter employs the internal battery in order to push current through whatever it measures, like a resistor or some other component. So when you join the leads together, when you have this meter set in the ohm meter setting, then the needle is going to swing out all the way to the right, suggesting that when the leads are touched, there should be 0 ohms between them because the leads are touching. There's zero resistance between them. Now, there's going to be a little bit of a resistance on the contacts that you push in, connectors. There's going to be a little bit of resistance on the leads or whatever. That's just a little tiny bit. So it's never going to be a completely zero, a true zero, because you're connecting things. So that's why you calibrate things in order to, because you want to see the resistance between the two end points of the leads. So that's where you are calibrating that to be is the zero. So what do you do is you use this adjustment control here. It says 0 ohms adjustment. What do? You touch the leads and the needle is going to deflect completely all the way here, but it's not going to be all the way. It's going to be somewhere here, usually something like that, or sometimes it's going to be somewhere here. So what you do is you adjust this after you have calibrated this thing mechanically here by doing this adjusting screw. Then you touch the leads, let the needle swing out all the way to the right, and you're going to use that adjustment control to calibrate that, so there is an indication of 0 ohms between the end of the tips of the leads. Okay, and then you let it out. You basically detach the, just make the leads not touch each other again. You just pull them away from each other, and of course the needle is going to swing back to the well, initial position, which should be here because you have adjusted that already. Okay? And then you're ready to do the measurement. All the other scales are, like, for example, in this case, and you're going to be using different ohm meters, voltmeters, amp meters, multimeters. You are going to have to figure out how this particular meter works. So sometimes it's going to, okay, how is this arranged? It has those scales. Sometimes you're going to have scale of 500. Sometimes going to have scale of 20. It depends. Different manufacturers make the meters in a different way sometimes. Okay, so let's just take a look at how we can actually measure some quantities. Let's adjust this meter to be a voltmeter. Let's make it voltmeter, and let's put it to the range that is up to 50 volts. So we're going to go into the dial and turn the dial. Click, 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 click. DC volts. We are measuring, let's say we're measuring DC voltage, and we're going to use the up to 50 volts scale. All right, and let's say once we put the leads across, let's say a resistor that's in a circuit, let's see what voltage is across the resistor. And it happens that the needle swings out, let's say, I used the same example as last class at 8 o'clock, and the needle swings and stops right here. All right, okay, let's see what measurement can we do. All right, so the range is 50, right? Oops. The range is 50. Do we have a scale that says 50? Oh, look at that, we're lucky. All right, here's a range that's 50, and here is the scale that is 50. So basically we use the middle scale and we just make the reading. So let's see what is the voltage that this meter reads, and we're going to use the 50 scale because it is the easiest at this point. So let's see here, 30, 35, because from here to here there's 1, 2, 3, 4, 10 divisions. So is it 5 or 10? So let's say from here to here is 40. From here to here, it's going to be 35. So 1, 2, 3, 4, 5. Okay, so each division represents 1. Okay, so the number that's showing on this scale is 30. 1, 2, 3, 4, 5, 6, 7. So we have 37 volts. Let's write it down in the top right corner here somewhere. We have a 37. Here, 37 volts. Okay, you know what? I always keep asking you to write the units, so let me write the units. 37 volts, and I put, excuse me, the units in square brackets. All right, so we have 37 volts. Where's my mouse? Let's write it down out of the way because we're going to do some more writing here. So again, we have 37 volts that this meter reads on the range of 50 volts DC, and we're using the 50 volt scale. But what sometimes, why do we have different scales? Well, excuse me, look at that. Here is my pointer. Here, for example, is a scale of 100. We don't have a range of 100. We don't have 100 here. Can we still do the measurement? Yes, we can. We have a 500 range. We don't have a 500 scale. Can we still do the measurements? Sure, we can. Let me demonstrate how. You can use any scale that you want to do that measurement, and depending on what scale you choose, you're going to have to apply some different numbers to it. You have to approach it in a different way. I mean, you're going to approach the same way, but you're going to apply different calculations. So let's just look at this thing here. We have a 50 range and we have a 50 scale. So it's 1 to 1. So whatever you see, that's what you get. All right. Now, let's see if we can get the same, if we can read the same thing using a different scale. Well, that's the whole point, having different scales. You can choose whatever scale. In this case, 50 to 50 was the easiest. But let's see if we can get the same amount of voltage showing using the 250 scale, while we have the 50 range and the needle deflected this far here. Right? Now, the easiest analogy that I can come up with is if you go to a flea market and you buy a bunch of potatoes, they will throw that on a scale in order to weigh it. So you throw things on the scale. Just so you remember what to divide by what to get the multiplier. And well, there's a mouthful, but you'll understand in a few seconds, a few couple minutes, you'll understand exactly what I'm talking about. We need to know, because we're going to get a certain reading, but the voltage across these 2 points is 37 volts. So we have to know that it's 37 volts. Just because we're using different scale, the voltage that we are measuring is not going to change. We're just changing the way we are reading it, but we have to come up with the same result because it is what it is. Right? So let's see if we can use a different scale to get the same result. Remember, I said you throw things on the scale. You don't throw the scale on the potatoes. You throw the potatoes on the scale. So you throw things on the scale. So here's a range. We are dealing with the range, and we're dealing with the scale. So we throw the range on the scale. Right? So we have a range of 50, have a range of 50, and we throw it on the scale. Let's say we choose the 250 scale. So we throw it on the scale of 250. There. All right. So let's see if we can come up with a number here. Anybody can get a calculator and see what what the number is? Anyone? Somebody's got a calculator. Oh, Marty, thank you. We got 0.2. Yes, it is correct. Congratulations. Now, 0. Let me just make it the dot. So 0.2 is our multiplier here. Okay, that's our multiplier. Now I'm going to use the term that's multiplier in this case. And in this case, when we're doing the measurement, the multiplier means this. You throw the range on the scale to get the multiplier. What is the multiplier in our case here? The multiplier is the number that we multiply, as the name multiplier suggests, we're going to get the reading on that particular scale that we're using 250, and we're going to multiply it by the multiplier to get the final result. So there's also going to be another multiplier that I will introduce you to, and it has something to do with bending conduits or the pipe bending, and we also use something that's called multiplier, but it's not the same thing that we use here. Well, let's concentrate on this here. All right, so we established the multiplier in this scale in this range is going to be 0.2. All right, let's see what the reading on this scale is. So we got from 0 to 250. So we have 150. Let me just get a better pointer here. So we have 150 here and 200, and we're using that scale. So between 50 and 200, that's got to be something like 175. It's got to be here somewhere in the middle. So let's see what each division is worth. Let's see, 75, 150, 155, 160, no, 151, 2, 3, 4, 5, no, 155, 60, yeah, it's going to be 5, 155 plus 5, 60, 65, 70, 55, 55, 60, 65, 70, 75. So each one is worth, each division in this case is worth 5. All right. So 175, 180, 185. On this scale of 0 to 50, we get 185. Okay, well, let's do the magic here now. I'm going to get a pen. So we're going to use that multiplier to throw it against that number that we are reading, which is 185. So 185, and we're going to multiply it by this multiplier here by 0.2. And let's see what the number is. Can somebody give me the number? 37. Well, 37. And what do we have? Always remember the units, volts. Okay. All right, so we read the same thing on two different scales. Let's just, for kicks, let's just do the 10-volt scale. What would be the multiplier? Okay, remember what we do? We throw the things on the scale. What do we have to throw? If we throw the range on the scale. So the range is still 50. Let's use the scale that's 0 to 10. So we throw the range on the scale. So we have 50 thrown onto 10, so 50 divided by 10, the multiplier is 5, right? We throw the range onto the scale, and 50 over 10 equals 5, so 5 is our multiplier, right? All right, so what is the number that we are reading here? The number is 0 to 10, so here's 6, here's 8, so that's gotta be 7. 1, 2, 3, 4, 5, 6.2, 6.4, 6, 8, 10. So it's worth 0.2, right? So 6.2, 7.14, right? 6, 8, 10. So 7.4. So let's get, we know what we're going to do. We have 7.4 times the multiplier, which is 5 in our case. Result, please. 37 volts. There we go. Equals 37 volts. Now, this is guys, how you use the multimeter. And I'm going to ask you some questions. I'm going to have pictures of needle deflecting and see if we can come up with the correct answers. But the most important thing is, to me, is that you get the idea of how to use these scales. I just showed you the voltages, but it also works with the current, and it also works with the AC. You know, an analog readout is an analog readout. And now I gave you the jumpstart on how to use that. All right, so let's get the meat and potatoes for today's week. We're going to start with the supplement first, because, well, yeah, I need you to understand what we're talking about as I'm carrying on the proper lesson, the main lesson. Uh, those documents, all these documents, please make your way to the class portal under the student sections of the content. And all these are going to be available for you to download. It's just in this class, I post them and make them available to you after I do the class, not before I do the class. All right. So this is going to be all those today's materials will be available for you to download. Well, in about half an hour. Okay, so let's see what the difference being, because we're talking about cable types. Let's see what the difference between a solid core wire and the stranded wire is. Well, as the description says, a single strand, what a solid core wire is. Description. All right, single strand. Okay, solid core wire is a single strand or core of wire insulated with a non-conductive material. So here's a why. It doesn't have to be insulated, because if you have the bare copper for the ground or bond, then it's a bare copper. It still is a solid wire. What about the description of a stranded wire? Well, it's a bundle of small gauge wires. Gauge is a descriptive for thickness. And it's a British system. It's like some called imperial system, and the gauging was I think it was invented during the some sort of 1812 or maybe earlier, the for the firearms. Right? And how things were gauged, sized, was there was a certain container and there was a certain size of the balls or lead balls. And if the container would be bigger, it would fit more of those lead balls. And if it would be smaller, it would fit less of them. And that's what, so let's say if there was the thickness of the gun barrel of a certain diameter, it would fit 12 of those lead balls. That means that thickness of the gun barrel was called 12 gauge, hence comes a 12 gauge shotgun. All right. Now, if the thing was bigger or smaller, then you would fit more or less of those things in there, and the gauge would be numbered like this. So gauge talks about thickness. All right, these were the old times, I think, and somehow some of that stuck with us. All right, so gauge talks about thickness. So bundle of small gauge wires, which right here you can see a bundle of smaller gauge wires, gathered in a bundle, and then insulated with a conductive material. All right, what do we have here? Usage. Where do we use these? The solid core wire is used mostly in the household and commercial installations. Permanent installations, typically it's a typical in-wall power cable. So when you're installing an outlet or a receptacle or do household wiring, you are going to be, for the most part, you will be dealing with the solid core wires. Right? Now, what's the usage for the stranded cables? Yes, can you wire up your house with a stranded wire? Yes, you can, but it would be a little bit less than practical, simply because, well, one of this thing is the money, because it takes more money to produce. It's more expensive to buy the same a wire that will do the same thing as solid core, and it's more expensive to produce because first you have to produce a lot of these smaller gauge wires, and then you have to bundle them together, and then so there's some extra steps of production. But why do we bother having them at all? Well, let's see here. Used for permanent mount, so that they are being used, and you see here moving or vibrating parts. typically in industrial equipment cabling. Why do we talk about moving? Okay, well, if the wire is stranded, it doesn't carry the vibrations as well as it would, as the vibrations would be carried in a solid core. So it is more practical to install them on the vibrating parts. So if you lift the hood of your car, you are going to find stranded cabling there. You won't find any solid cables. Then in industrial machines, the machines work, rattle, and shake and vibrate. You're going to see if you decide to go for the industrial electrician position, then you will be dealing mostly with the stranded. You'll be dealing with a stranded wires a lot. Okay. All right. Advantages and disadvantages. Solid core is less expensive to produce, and it takes less space for the same current carrying capability or ampacity. Well, in order to carry a certain amount of current, you have to have a certain amount of copper. You have to have a certain amount of meat on that cable. Right? Well, in a solid core, everything is nicely compacted, so it takes less physical space. If you want to have the same current carrying capability or capacity or ampacity, then you're going to have to use the same amount of copper. Well, the same amount of copper in stranded, physically it's going to take more space because you are bundling those small pieces and there's air gaps between them. So yeah, so basically it's going to, the whole wire, physically it's going to be looking thicker for the same gauge, right? So 12 gauge solid wire is going to be physically thinner than the same gauge, 12 gauge stranded, right? So that's why it takes more space or less space. Okay. And it is less likely to fail due to corrosion. Well, look at it. What is exposed to elements? There's certain area that is exposed to the elements and everything else is just inside. Well, in the stranded wire, you have more area or areas, if you can say that, exposed to the elements because that wire is broken into pieces. So more area of the same amount of copper is exposed to elements. So yes, this wire will corrode quicker than the solid wire. All right, so we're talking about advantages for the solid core. Typically only available in small gauges. It's a disadvantage now. Why is that? Well, if you look at it, when you make this wire thicker, and sometimes those wires get thick, right? A few inches. Once you get the solid core wire thick enough, you're not dealing with a wire anymore. You're dealing with a piece of metal rod, which is harder to route, harder to bend, and harder to adjust its physical layout. Well, when you talk about the stranded wire, if you make them thicker, they still would maintain at least a little bit of the flexibility. It's not going to be as flexible as very tiny thin wire because tiny thin wire is just like a string. Heavier wire is going to flex less, but it's still going to have a little bit flexibility as opposed to the solid core wire. So that's why. Now, let's continue with the disadvantages. Continuous flexing or vibration will cause the wire to fatigue and break because it's a solid wire. You move it around and it's going to break quicker. This what I'm talking about, the stranded wire, well, it's got a little bit of a give, so it is not going to break as quick as the solid wire, right? But it is more likely to fail the corrosion, which we already talked about. Let's just quickly go over advantages and disadvantages of the stranded wire. We already got that. Advantages: very flexible and withstands greater amount of flexing and vibration. Easier to route because it's more flexible, so it's easier to lay. It's easier to install. Diameter is disadvantages. The diameter of the wire is larger. We talked about that. More costly to produce. We talked about that. And it's more likely to fail the corrosion. And we talked about that. All right. Now the rest you can read here, and it's mostly now gauge. How do we read gauge? Gauge is the descriptive for thickness of the wire. It's AWG, American Wire Gauge. Well, sometimes you will hear that on the construction site or on the industrial environment. Can you bring me 12 AWG? But you see how long it takes to say that, to pronounce that. So it just generally said that if you see that number, like say 12 and this AWG, you just read it, you just read that as gauge. Right? So that's just a little heads up on the terminology. Right? All right, let's go to the next document here. Cable types. What do we have here? Here is a 2-wire cable. Here's a 3-wire cable. Here's a 2-wire armored cable, and blah, blah, blah. All right, what do we see? What do we see here? On this cable, we see a designation that says 14.2. Well, 14 stands for the gauge. And here's the thing. The bigger this number, this 14 number, the bigger this number gets, the thinner the wire gets. And the smaller that number gets, the thicker. They're inversely proportional. The gauge goes up, the number goes thin. The gauge goes down, the thickness of the wire gets thicker. Right? And now here, there's that 2 that says it has 2 conductors. So let's count them. And as I said last time, there are 3 kinds of people in this world: the ones that can count and the ones that can't. All right, so let's see here. 14.2, that means it's 2 conductors. So let's count the conductors. 1, 2, 3. There you go, 2 conductors. It's still 2. What does it mean? Is that when we mean that 2 number here, we are talking about something that's called a current carrying conductors. These are the ones that are busy under normal conditions, which means there's nothing wrong. There is a wire that is supplying the power to the receptacle, and we have a TV or a fridge plugged into the receptacle, and things are happening. All right, the current is flowing. So these are the current. So the current will flow. Here's the thing: the black is hot, the white is neutral. The white is always neutral. Then there are different colors, and they're going to be hot. So in this 14.3, we have 1, 2, 3 current carrying conductors, and we have a ground wire or a bond or bonding wire. The difference between grounding and bonding is, let's say there is, and I couldn't find the grounding strip here on this panel. There is somewhere there's a grounding strip. Right? I think it's this one right here. And here's the neutral bar. If this grounding strip has a wire that runs directly into a true ground, and a true ground could be a spike driven into the ground outside in a specific way that coincides with the code. It could be a metal plate buried in the ground that fulfills the specifications of code. or it could be a designated terminal in the electrical room that is labeled as true ground. So if from that bar there is a uninterrupted wire that goes nowhere else but to the true ground, then we can say that this panel is grounded. Right now, let's see. From this ground, there will be wire going from that panel, from the circuit breaker, to a receptacle. From that receptacle, it's going to go to another receptacle, and from okay, you'll get the idea. That receptacle that is here, that that receptacle that would be here, it's also grounded, so to speak, but the wire that goes from the grounding terminal of the electrical box and the grounding terminal of the receptacle is not going uninterruptedly to the true ground. It goes to this bar here, and that bar is grounded. So the electrical potential, it still has the value of the ground, but we use the terminology that because it is not going directly without any interruptions to the true ground, it goes through the true ground, but first it goes through some other device, and there's a connection there. Then we call it that this is bonded. It's same as grounded, but it's bonded, and that's how we distinguish between bonding and grounding. Okay? So sometimes I'm going to use the grounding wire. Sometimes I'm going to say the bonding wire or bonding terminal. All right. So how is it that some of the conductors are supposed to carry the current and some can't? Some are not meant to carry current. Well, all of them are meant to carry current, but here's the key, as I said before, under normal circumstances, under normal conditions. The grounding wire or bonding wire is a safety feature that is part of the system. How does it work? That it's a safety feature. Let's say there is this wire here, 14.2, which is 14 gauge, 2 current carrying conductors, and the grounding wire is not counted when specifying the designation of the cable. Right? Again, I'm going to say it again. 14 gauge and the 2 means 2 current carrying conductors, not counting the safety wire, which is the grounding wire or the bonding wire. Under normal circumstances, there is going to be current leaving the hot, which is the black. White is always neutral. It's going to go through whatever load it is going to go through, and then it's going to return to the electrical panel through the neutral, which is the white. The circuit is closed. That thing here, this neutral, this grounding wire, the safety wire, is there, but it's not working. It's not employed to do the work. This one here is supposed to kick in when something goes wrong. Why is it? What could go wrong? Let's say you have electrical box and it's a metallic electrical box, and for some reason that becomes detached from the screw terminal, and it just spring loads itself and rests against the metal chassis. Well, if that metal chassis is not connected to anywhere else, then that basically becomes same potential as the hot. And if you come towards that outlet or the box, the electrical box, and you touch that with your one hand, and your other hand could be touching something else like kitchen sink that basically is grounded, or something else, or you could be standing on the floor that is grounded. Well, floor is grounded, is potential of a ground. You could get electrical shock, or you could get electrocuted, right? Electrocuted means you're dead. If you get electrical shock, you're shocked by electricity, right? So then if you touch that box, which is basically powered by that thing touching it, then the current is going to flow through you. through the shortest path, and it could flow through your chest. Well, that's where your heart is, and yes, it'll affect your heartbeat. It can actually stop your heart. It can flow through your limbs, through your leg. You can go hand to leg, hand to hand, leg to leg. It can go from hand to leg, which means that it might actually go through your stomach. And stomach has different chemicals in it, mostly acids and whatever liquids, and you have electricity passing through it. It can cause some of the chemicals to break down into different chemicals, and you actually, there is a possibility that if you get electrocuted, if you get shocked um, by electricity and it flows through your stomach acids long enough, it'll actually create some things that will be harmful to you. So you could die from poisoning while being while going through an electric shock, right? So well, how do we solve that? That we eliminate the possibility. Well, we never eliminate, there's no guarantees, but we do whatever we can to do, and they do a pretty good job. We connect that bonding wire to the metallic box. So what is going to happen? That box is going to be grounded or connected to ground, or bonded, which is also connected to ground. So now when this wire touches that, the electricity has somewhere to flow. It's going to flow to the ground, and it's going to flow at such a high rate, it's going to basically flip the circuit breaker. It's going to shut it down. So that's a safety feature. Right? All right. So what do we have here? So 14.2, how many physical conductors? Well, 3. Why is it 14.2? Because we are talking about current carrying conductors. And what do we mean by that? It's that under normal circumstance, under normal conditions, these are the 2 that are meant to do the work. This one here is just waiting to kick in if something goes wrong. And we just explained. All right, so here is an example of 14.3. How many wires? 1, 2, 3, 4. But we have that bonding wire that we don't count while we're talking about the designations. What do we count? Is the current carrying conductors. Again, we have the neutral, which is white, always white. Then as the first one, we have the black for hot, and we also have the red for hot. Okay. Now here's another example of a cable that is called an armored cable. Sometimes it's called MC for metal cladding, metal cladded or metallically cladded cable. Cladding is, well, coating, surrounding, so it's coated with metal, all right, surrounded by metal. And sometimes it's called the armored cable because that metal surrounding or metal cladding is arranged in a certain way physically that it actually acts as an armor. So that thing is being installed in some rougher conditions. So here's a 2-wire armored cable, and it can have the ground or not. Sometimes you're going to see the terminology as BX. And although it's not an official term, you will not find the terminology in the code book. However, you're going to hear that a lot. Just give me 10 feet of BX. We need to run BX cable in on this wall because whatever, right? The BX stands for cable type B, experimental. So when the cable was being invented by, I forget whatever the company was, then they called it the experimental stage. They called the experimental cable, and they designate as cable B instead of cable A. So that's why sometimes you're going to hear the BX. Not a big philosophy, all right? That's why sometimes you call it BX. We're going to skip the fasteners and connectors because, well, I'm going to keep introducing them to you as we go along in the labs. There is like there are tons of them, and yeah. So here is another example of UF, right? That says for underground feeder cable. Right? So that means this cable can be installed underground because of the way the jacketing is constructed physically and chemically. Sometimes you're going to see something that you have with the designation of B as in Bravo, and that stands for burial. So underground feeder direct burial cable, which means that if it's a direct burial cable, you can just dig a trench and throw that cable right in and cover it with dirt. Of course, there are certain procedures that you have to follow, but you don't need any additional conduits, pipes, or whatnot. So if you have the underground feeder direct burial cable. There are different kinds of it. Now here's the gauge explained. I'm not sure if you can see that here. There's a 10 gauge, there's a 12 gauge. Remember, I said as the number goes down, the gauge goes up. I mean, the thickness goes up. So the gauge goes down. So here's 10 gauge, the wire is thicker. There's 12 gauge, the wire is not as thick, it's thinner. All right. And you can click on here once you download that to find out more. Want to find out more? Click here. That's the next one here. Now, over here, we talked about that solid core wire, stranded wire. We talked about this whole supplement that is available for you, and we talked about it right in the beginning. Multi-conductor cables, and there's that NM, non-metallic sheathed cable, and this one is 12-2. How can we tell? What can we tell about that when you see the 12-2? Well, we know the gauge is 12, the thickness of that is 12, and there are two conductors, two current carrying conductors. We don't count the ground wire or the bonding wire. Here is a 14-3. That means there is a gauge 14 conductors, and there are three current carrying conductors, and there's that not counted bonding wire. Now, 14 gauge, 12 gauge, which is thicker? Well, the 12 gauge is thicker because as the gauge goes down, the thickness goes up. And here is a large appliance stranded cable, or there's a solid grounding, but a stranded wire. And here's that MC. Remember I said, what does the MC stand for? It stands for metal cladding or metal cladded. What's cladding? Surrounding, coating, whatnot. Right? Now, when it comes to grounding or bonding wire, the rules are in North America, excuse me, that you can either have them in green jacketing or bare copper. Right? So that's the ground wire or bonding wire. And then neutral is always white, and all the other colors are going to be, it's going to be hot. They're going to be hot wires. Gauge is explained. As I said, you can just look at the picture and remember what I just said. As the gauge goes up, the number goes down. Now, are the cables available in all different gauges as we talked about? No, the solid wires only go up to certain gauge. Normally, yes, there could be some special order for some special situations. So you can say, oh yeah, but I saw. Yes, okay, I saw that too, right? But normally, the the solid gauge, they normally they go to like a gauge 10, and then we start gauge number 8, the wires go thicker. And as I said, if you go thick enough with the solid core wire, you're dealing with a metal rod instead of a cable. Now it's 4 minutes to 4 minutes to the end of the class. If you have another class to go to, by all means, please go. I'm going to post this on YouTube, so you're going to be able to see the end of it. We're going to, in this week, unfortunately or fortunately, you put it as you will, we're going to go a few minutes above the timing. So you're welcome to stay, or I'm not going to get offended if you leave because you have to go to another class, and you can catch the end of it as I post it on YouTube. All right. Now, household wiring here. Let me see here. There we go. Household wiring. And I'm going, sometimes I read. Okay, so the most common household wire, the most common type of cable in household is technically known as NMD9D. The NM stands for non-metallic. The D stands for dry service cable. So it is supposed to be, well, it is a non-metallic sheeting or coating or jacketing, and it's also meant to be installed in a non-metallic on a non-metallic surface. So if you have steel framing, you can't put directly that cable directly against that steel framing, you're supposed to either run a conduit and pipe, and then, well, then you can use metallic conduit, but or PVC, but you can't mount that cable directly against the steel studding or steel framing. Now, sometimes if you just have a little short run to do, and that's all the cable you use, and you have to run through the steel frames, sometimes you just mount like a wooden 2x4, and you fasten that to the steel stud or steel frame, and then you attach the cable to the wooden structure, that, well, the wooden piece of, well, wood, right? So that's so dry service. And here's the 90, which means it's rated to be able to handle 90 degrees Celsius, not Fahrenheit. What's the water temperature for boiling in Celsius? It's 100 degrees Celsius, so it's just 10 degrees less. What's our body temperature in Celsius? Is 36.6 degrees Celsius. So, well, you get the idea, right? Now, of course, it probably is going to handle slightly more, but it's rated. Well, that means we're not allowed to install things that are not rated for whatever the environment is. Now, also the brand name that is commonly called Romex. All right, so NMD90 is the non-metallic dry service, and that's the ones that we're playing with during the labs. It's called non-metallic dry, NMD90. Some time ago, well, a few years, maybe more than a few years ago, the only company that had monopoly on production of this wire was a company that was called Romex. So that's why sometimes you're going to hear Romex. Just like, I don't know, sometimes you would hear, instead of, can you make a photocopy of these papers, like, can you take those papers and photocopy them? You're going to say, can you Xerox those papers? It's just like Xerox is a company, it's a brand name. So same thing like that, right? So there you go. The cable is usually configured in 2 or 3 conductor combination. That means current carrying. 2 conductor having a black and white. White is neutral, and the black would be the hot wire. And we have a bare copper wire for the ground or the bond. Right? We all know, by now, we all know what the difference is between grounding and bonding. The bare copper wire is never counted, or the grounding wire is never counted as in the conductor count. 3 conductor has black, red, and white conductor, and a bare copper wire. So the conductors are most commonly 14 gauge. This cable also comes in 12 gauge. Right? Now let's see here, household wiring. Let's see, most commonly used cables and their uses. 2 conductors, so it would be 14-2. Okay, 14-2, mostly used as plugs, switches, lights. It is roughly about 70% of your household wiring. If you have all the electrical wiring in your house, about 70% of that will be this most commonly used cable. Then 3 conductor. It's used in 3-way switches, which we will study later on in this course, and split receptacles, which we will study later on in this course. If you want to get heads up, well, you know what? You got Google, you got YouTube. you can research that ahead of time, or you don't have to. We are going to go through all that as we go along. Okay. All right, most commonly used. So that was 14 gauge. And there's one thing that doesn't say here. It is rated for 15. The ampacity. Ampacity is current carrying capacity or current carrying ability. It is rated for 15 amps. Okay. If anything requires more than 15 amps, we are not allowed to use that cable for it, because it's going to heat up and it can cause problems. Now, 12-2. See, the gauge is 12, which is the lower number of the gauge, which means the thickness goes up. So 12 gauge is thicker than 14 gauge. Now what do we have? Selected heaters. Okay, well now we're basically, well, cooking with electricity. All right. Selected heaters, air compressors, anything that uses maximum of 20 amps, so 5 more than the 14 gauge. Is it going to handle more? Probably, but we're not allowed to install anything that is not rated for whatever the purpose is. And kitchen receptacles and circuits. Usually kitchens require a little bit more amps. Just imagine in the morning, everybody wakes up and there is that toaster going, there is that tea kettle going, there's whatever else, let go my ego kind of a thing, whatever it is, and people plug those things in at the same time. The wires work hard, so sometimes gauge 12 are being chosen and mandated to do, depending where you are. Then here's three conductor number 10 gauge, which is even thicker. Any device that requires more than 30. Okay, so 30 amps for gauge 10, 20 amps for gauge 12, and we have 15 amps for gauge 14. All right, then that will be any device that requires more than 30 amps. The most common application would be electric dryer. Right? Now, with three conductor 8, maximum of 40 amps, the most common application would be electric range, which will be electric stove. There you go, 40 amps, thick wire. All right. Now, is it the last slide? No, it's not the last slide yet. As a checkpoint, household, well, okay, not a checkpoint. Here's the thing, household wiring, house wiring. Is it done in series or in parallel or whatever else way, maybe as it's needed? We already know what the difference is between series connection and parallel connection. So let's just visualize things. New. Let's get a clean page. All right. No, no, no. Create. There we go. All right, so let's see, let's get some color that is going to be noticeable. And get a pen. Let's say we have the black, which would be the hot wire. Let's say we have the white, which would be the neutral wire. And let's say we have the bonding wire or grounding wire. Okay, all right. So what's the pathway? It goes from hot, the current goes from the hot, goes through whatever load, let's say a fridge at the end, and comes out of the fridge and returns to the neutral. The current pathway has to be closed. We have to have a closed circuit. So let's say if we connected the receptacles in series. So here's a receptacle. Here's a receptacle. Here. Here's a receptacle. And let's say another one. Here's a receptacle here. All right, so we go from one, and then from the other terminal, we connect here, we connect it here, we connect it here, and we connect it here back to the neutral. Well, if nothing is plugged in, there's no current flow. Well, let's say if we, if we have a TV on one of the outlets, all right, so the current is going to go through TV, right? All right. Let's say another one is going to be a vacuum cleaner, right? As a vacuum cleaner. And then another one, whatever else, and there's one that has a fridge on it. Well, all of those devices have to be turned on in order for the current to have a path to flow through. If there is anything that is not connected, let's say over here we have a, I don't know, a light. All right. So, and there's the fridge. In order for the fridge to work, you would have to have a TV on vacuum cleaner on and the light has to be on for the current to have a closed return path. That would not be very practical. So series is not. Now let's go hot, neutral, and ground. And if we go like this, right? And here is the outlet, here is the outlet, here's the outlet, and they're connected as such, like this, and like this. And those devices are connected in parallel to each other. You can just keep connecting them as long as you don't over exceed the allowable number of receptacles. Uh, well, if you plug in anything, you can plug in the fridge here, and nothing else has to be plugged in because you're going to provide the close path to the neutral. Right? If we plug in the TV here, that's fine. You can also, so the household wiring has to be done in parallel and not any other way when it comes to connecting receptacles. And here, I'm not going to go through all of that. Here's an example of things. You will be familiar with one and each of of these devices as you continue your journey through our program. But just have a read through that. Okay. Typical housewife. Can you identify a common device that is missing by law? Blah 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 blah. Okay. Well, right now you have to have a smoke detector in every room, right? So yeah, it's one of those questions. Yeah. All right, I think that's the last slide. Yes, it is the last slide. We go 10 minutes after. All right, service conductors. There are specific cables used to carry the power into the house to service panel, to the service panel right here. Here's the service panel. All right. These are referred as to service conductors. What are service conductors? They are conductors or wires or cables that are providing power. What other cables can we have that are not providing power? Well, let's say a microphone cable, that would be a signal cable, things like that, right? So you are not going to get lots of power to your household through a microphone cable, right? So that's why, we distinguish that service conductors or service cabling, service cables are the cables that provide power. Now, service conductors that are run overhead are generally made out of aluminum. And if you're English, you would say aluminium, right? And you're from Europe, you're probably going to say aluminium as well. But over here, we say aluminum. Anyways, whatever you call it, it is the same alloy. It's the same type of a metal that we use for, these are overhead. Where's the overhead? Service, yeah, overhead. What is an overhead cable? Well, here's an overhead cable. Here's the house. Here's the service panel. And there is overhead cable, which is going over your head, suspended, and it goes to the hydro pole, to the connection point right there. So that's what's called overhead. Now, is it better to use in the household wiring as far as the conductivity and general longevity? Longevity means how long is it going to last. Copper lasts longer, it conducts better. It doesn't heat up as much, and if it heats up, it's not going to deteriorate or get damaged. Aluminum is also a pretty good conductor, but it doesn't last as long as copper and things like that. Right? But so why do we use aluminum cable to suspend the wires overhead while providing power to households? It is the weight. Right? Aluminum is much lighter, and just to think about it, if you add the weight of the cable, sometimes the distance is not that short, and sometimes it doesn't have to be that long for the cable to actually bear its weight. It could be heavy cable, so the aluminum is lighter. That's why the service cables that provide power to the households that are hanging overhead are going to be made out of aluminum because they are lighter. And that's the reason for that. Underground, well, no problem, you get copper. All right, so we went 13 minutes over the time, and I apologize for that, but it's going to be well worth it for you later on as you leave the school, because the more information, the more knowledge you get, the better you are. And there's a phone ringing. Um, somebody pick it up. Somebody pick it up. Pick up the phone. Okay, somebody picked up the phone. All right, cool. So that concludes our lesson for today. And I will see some of you during the labs this week. And some of you I will have the pleasure to see next time we see each other, which will be Friday. Okay, have a great week, guys. And I will see you when I see you. Thank you.